Hi, I'm Kewalin Samart. I am an undergraduate student majoring in computational mathematics with a minor in computational math science and engineering at Michigan State University. I'm currently working in the Jeravi and Krishna labs at Michigan State. Today, I'm very pleased to present our recent work on reconciling multiple connectivity scores for drug repurposing. Computational drug repurposing has been an efficient alternative for drug discovery since it is both cost and time effective compared to the traditional ways of discovering new drugs, which requires a significant amount of time and budget, also a very long and complicated process. Computational drug repurposing helps us discover new drug indications based on the existing regimens. Infectious diseases continue to cause ill health and death to millions worldwide, despite advances in public health over the last 100 years. As the Jared Lab focuses on developing computational approaches to study infectious diseases, the drug repurposing project is one of our ongoing projects that we develop a computational gene expression-based drug repurposing framework to fight infectious diseases. The essential concept of this approach is to identify drug candidates that can successfully reverse the disease signature by comparing disease and drug transcriptional data. Basically, the efficacious drugs are the drugs with reversal relationship to the disease. Essentially, we measure disease-drug association level using the concept called connectivity mapping, where we start with a ranked order disease gene list. Then we separate the disease genes into up and down regulated gene sets and compare the two disease gene sets with a ranked order drug gene list. The level of disease-drug connectivity is determined based on differential expression values, position, and membership of disease genes in the drug profiles. Negative connectivity, which indicate disease-drug reversal, is defined as the case when the disease signature shows dissimilar perturbations. This occurs when upregulated disease genes appear towards the bottom of the drug profiles, or downregulated genes appear towards the top of the drug profiles. Back then, when my teammate and I was reading research on disease-drug connectivity scores, as we trying to figure out what would be the most efficient approach in computing disease-drug association score to apply in our project. We have found that in the past decade, many methodologies have been developed with the claim towards improving robustness and accuracy of the previous ones. In this figure here, we're showing a brief history of connectivity scores and metrics that have been proposed by different studies over the past 15 years. Unfortunately, these existing methods have been described using inconsistent notation and terminologies, although they have been built upon a shared set of mathematical, statistical concepts and ideas. So it is difficult for us to understand and interpret the connections among the different scores, also difficult to compare, benchmark, and build on. Here we have a couple of examples where different papers use different notation to refer to the same terms or quantities. On the left, we have the SCA method developed in 2005. They refer to the enrichment score as ES, but in CMAP 1.0 method, refer to the enrichment score as KS. Another example is the notation for number of drug genes in the drug profiles. In the SCA study, they use capital N, but in CMAP 1.0, they use a lowercase n. In order to address the inconsistency issue, we came up with a unified set of notation for all the fundamental quantities and terms that are used by all the methods. And this is the final general notation table that we came up with. And we use this general notation to redefine all the scores. Then we use the general notation to re-summarize all the formulations of the existing methods and establish their relationships to gain deeper mathematical and statistical insights into each score. We did redefine all the scores using our new notation, but today I will only walk you through how we were able to relate the popular GSEA and CMAP 1.0 methods as an example. By using our unified scheme, we were able to establish a clear connection between the GSEA and CMAP 1.0 enrichment score. That the CMAP 1.0 enrichment score is the adapted version of GSEA instead of comparing the position of disease genes to the non-disease genes in the drug profiles, using a side two-sample Kolmogorov-Smirnov test. CMAP 1.0 uses a side one-sample Kolmogorov-Smirnov test to compare the empirical distribution of the disease gene position in the drug profiles to a reference uniform distribution of disease genes in the drug profiles. After attempting to develop a new set of notations, redefine and connect all the existing methods, we realized that this exercise can be really helpful and valuable, not just for us, but also for the community of computational drug repurposing researchers. So we decided to develop this into a serious operation. And finally, we constructed a taxonomy of all the connectivity scores, which lays out the relationship between ideas and methods. In panel A, the second column shows all the different disease drug connectivity scores that have been developed and applied in computational drug repurposing research with successful outcomes in clinical trial in the past 15 years. With our new consistent notation and terminology, we have noted that all of these methodologies were derived from different choice of disease drug similarity metrics. We have two main similarity metrics. The first one is the enrichment score, the other one, namely pairwise similarity metrics. The score that computed based on the enrichment score are built upon different kinds of Kolmogorov-Smirnov statistics, as I mentioned before in the previous example. For the pairwise similarity metrics, they're computed using different shared genes expression values and various mathematical similarity calculation. Then in panel B, we have fundamental mathematical formulation for each of the connectivity score redefined using our new notation. To ensure that everyone who reading our work can relate our new notation to the previous one in the original study, we also provide notation table like this for every single approach. After redefining all the methods, we got a scheme to interpret the meaning of the scores. Basically, different scores can be easily interpreted through the size of similarity metrics. The favorable outcome that the drug can fully or partially reverse the disease signatures are the cases that we have negative enrichment scores for disease upregulated genes or positive enrichment score for disease downregulated genes and negative non-enrichment scores similarity measures. These three scenarios correspond to the two cases in the middle, where we have upregulated disease genes mostly distributed at the bottom of the drug profiles and downregulated disease gene mostly distributed at the top of the drug profiles. Our Reconcile score helped us reveal 4 biological and practical insights of the score, such as nature of reversal, choice of threshold for input disease data, amount of input information, and symmetry between disease and drug data. For the nature of reversal, a lower negative score indicates a better reversal relationship between the disease and drug. The second insight is the choice of threshold used to determine the genes most perturbed by the disease. This choice could be based on the level of significant p-value cutoff, fold-chain cutoff, or just rank all the genes based on their differential gene expression value and then select a desired number of top and bottom genes. Different choices of thresholds is likely to essentially influence the performance of each metric in prioritizing rare disease drug associations. The last two properties are amount of input information and symmetry. Different metrics require different input disease and drug data. For example, some require a full set of genes. Some require only a set of the most perturbed genes. Some require a rank order list of genes, and etc. Such variation of input affects the symmetric properties of each similarity metric. The ones with symmetry can be directly applied to not only just disease-drug association, but also to quantify disease, and drug-drug relationships. All the similarity metrics and connectivity scores described here have not been systematically benchmarked and built on the large scale. However, these comparative studies have shown that simple metrics like X-sum and X-cos outperform the enrichment score-based methods. The E-Mudra score, which is a combination of multiple metrics, as expected, it performs better than any single metric alone. Another study found that the performance of the enrichment score and the connection strength score CSS depends on the number of genes in the disease signature. And the rank-based methods could suffer from distribution genes with high rank, but not substantially differentially expressed. In conclusion, the methods proposed in the past 15 years have been built upon each other over time, thus addressing previous limitations, leveraging larger amounts of data, and achieving better performance in prioritizing repurposed drug candidates for diseases. Therefore, they have shared a number of core conceptual and analytical ideas, also use similar statistical techniques and quantities. However, these different studies describe the methods using inconsistent notation and terminology when naming systems refer to previous method and mathematical details. Such variation is an impediment to cogent detailed understanding of current methods, their transparent benchmarking and evaluation, and the development of newer methods that continue to build on existing ideas. Our uniform schemes improve the consistency of future methods with existing ones, and help clearly establish the origin of analytical ideas, which make it easy for us to compare, benchmark, and build on. As you can see that our effort helped us gain the significant insights into disease drug connectivity scores. A project like this is also important for many subfields in computational biology because new methods have been continuously developed over time. For the continuous and transparent incorporation of newer methods, in addition to a traditional paper, we created an online live document and an accompanying GitHub repository that anyone can use to add detailed description of newer methods using the same notation. And here I will show you a quick look of our article that has been hosted as an online live document. We wrote this using our Markdown and distill package. And this is our GitHub repository, namely jrelab/connectivity_scores. Accompanying with the live document that any researcher in the drug repurposing community can build on and push changes to. I would like to acknowledge both of my fantastic mentors, Dr. Janani Ravi and Dr. Ajahn Krishnan, everyone in the J. Ravi and Krishna labs for their support and feedback on the work. Moreover, I would like to thank all the funding that support our project. And lastly, the ISMB ECCB Conference 2021 for the opportunity to present my research today. Thank you so much for listening.